There is no internet connection involved in what you are about to watch. No data center, no API key, just a file on a laptop. And a question. That is a 9.7 billion parameter model answering. And in the next 9 minutes, you will know exactly what happened between pressing enter and that first word. Here's the part nobody explains. You press enter. Something happens. Words appear. That gap in the middle is where every real question about AI actually lives. Why is the first word slow and every word after it instant? Why does the same model want 6 gigabytes on one machine and 15 on another? Why does the same question give you a different answer every time? Every one of those is the same gap. So we are going to open it. 4 steps: a file, a wake-up, a translation, and a loop. Step 1. On disk, a model is not a program, it is a file. This is the real one, on my machine. 6.59 gigabytes. If you open it, there is no code in there. There are numbers. 883 blocks of them. 9.7 billion values in total. And every single one is a setting that got nudged during training, and then frozen. That is the whole thing. A language model on disk is a frozen brain, not sleeping. Frozen. It cannot do anything at all while it sits there because nothing is running. No process, no memory, no state. It is a photograph of a brain. And this is the part that surprises people. 6 gigabytes. That is smaller than one modern video game. Everything this thing appears to know got squeezed into that grid of numbers, and none of it is stored as facts you could go and look up. There is no sentence about black holes sitting inside that file. There is only the grid. Step 2. Waking it up. When you type Ollama run, the first thing that happens is boring and expensive. The file gets read off the disk and laid out in memory. All of it. You cannot stream a brain. Every one of those 9.7 billion numbers has to be reachable, in any order, in nanoseconds, because the very next step is going to touch almost all of them. Disk cannot do that, memory can. So the whole file moves. On my machine, that took 2.5 seconds. Once. And now watch this number, because this is the one that decides whether a model runs on your laptop or not. On disk, 6.59 gigabytes. In memory, right now, 15. Same weights. Nothing got bigger. What got added is scratch space, a notebook the model keeps for your conversation. And that notebook is sized by how long a conversation you allow. Drop the context window from its maximum down to 4,000, and the exact same model asks for 5.6 gigabytes instead of 15. That one setting is the difference between fits and does not fit. Step 3. Your question is not text to it. Type a sentence, and before the model sees anything, it gets chopped up. This is the real tokenizer, pulled out of that same file. Explain a black hole to a 5-year-old. 11 pieces. Now look at the first word. Explain came apart. X. Then plain. 2 pieces. 2 different numbers. The model does not read letters, and it does not read words. It reads whatever chunks happen to be common in its training text, and each chunk is just an ID, pointing into a table of 248,000 of them. So by the time your question reaches the actual model, it is not a question anymore. It is 11 integers. That is genuinely all it ever sees. Which, by the way, is why it cannot spell. If the model has never been handed a letter, only a chunk, then asking it how many R's are in a word is asking it about something it has literally never seen. Hold that thought. There is a whole episode on it later in this series. Step 4. This is the engine. Those 11 numbers go in the front. They pass through 32 layers, stacked, each one reading what the last one wrote. Real numbers from that same file. 32 blocks, 4,096 values wide. And what comes out the other end is not a sentence. It is one word. One. So the model does the only thing it can do. It takes that word, glues it onto the end of your question, and runs the entire thing again. 12 numbers this time. 32 layers again. Out comes word 2. Glue it on. "13 numbers. Run again." That is the loop. That is all of it. Every word you have ever seen an AI produce came out of a machine that only knows how to answer one question. Given everything so far, what comes next? It has no plan. It has never seen the end of its own sentence. It is one word at a time, all the way down. On my machine, that loop runs about 80 times a second, and every single one of those passes just moved through 9.7 billion numbers. That is the bill the AI industry is paying. That is why they buy GPUs like gold. Which brings us to the thing you noticed on day one and never questioned. The first word is slow. Every word after it is instant. Here is the actual measurement. Cold start, 2.8 seconds before the first character appears. Then 12 milliseconds per word, steady, all the way to the end. Now run it again, without restarting. 0.2 of a second to the first word. Same model, same question, same machine. So the wait was never the model thinking. It does not think harder about the first word. The wait was step 2. It was 6 gigabytes moving off a disk. You were watching storage, not intelligence. So here is the whole gap, end to end. You press enter, a 6 gigabyte file is read into memory once and stays there. Your sentence is chopped into 11 numbers. Those numbers walk through 32 layers and one word falls out. That word gets glued on, and the walk happens again and again, 80 times a second until the model decides to stop. That is the entire machine. There is no other part. And you can watch all of it yourself in about 2 minutes. Install Ollama, pull a model, run it. While it is answering, open a second terminal and type Ollama PS. That is my machine, right now. 15 gigabytes resident, 100% local. Tell me in the comments what tokens per second you get and on what hardware. I read every one of those. One last thing before you go. Run that exact same prompt again. Same file, same weights, same math. You will get a different answer. Every step you just watched is deterministic. Multiply, add, repeat. And yet the answer changes every time. There is a dice roll hidden in the very last step, and almost everybody sets it wrong. Tomorrow, we go find it.